Hey guys, go ahead and get out your note sheet that says writing ionic formulas, and we're going to get started and get these notes down as quickly as we possibly can. So we're done with the periodic table. When I say we're done with the periodic table, I mean we won't be looking at it every single day like we did last 6 weeks. But now we're going to take what you've learned and kind of build on that. So we're going to talk about how individual elements on the periodic table can come together and make compounds, and how we can figure out what the names and the symbols for those compounds are. So here we go. Alright, so the first thing that you need to know is that compounds are held together by chemical bonds. So it's what holds the two elements together. They connect them together. Just like how, I don't know, stuff holds stuff together. Like, I can't think of an example. Just like how glue holds paper to your book. Okay, your chemical bond is kind of like your glue holding one element to the other element. Now, there are two kinds of compounds, ionic compounds and covalent compounds. Let's start by talking about the ionic compounds. So ionic compounds are made by metals and nonmetals. And I believe on your note sheet, you're supposed to just circle the right one. So ionic compounds are made by metals and nonmetals. It's what happens when a metal element bonds with a nonmetal element. They are held together, like we said, by a chemical bond, but it has a special name. It is called an ionic bond. So ionic bonds hold ionic compounds together. Ionic compounds are made of metals and nonmetals. In an ionic bond, the metal gives its electrons to the nonmetal. So remember when we talked about like group 1 and group 2 and group 3, and we said that they're +1, +2, +3, and that plus tells us that they're going to easily give away the electrons they have. That's what's happening in this ionic bond. The metal is giving its electron to the nonmetal. So I'm going to give you a couple of seconds to make sure that you have it all copied down for ionic compounds, and then we'll move on to covalent. So covalent compounds are made by two nonmetals. Again, covalent compounds are made by two nonmetals. Let's go ahead and fill that in. They are held together by a chemical bond called a covalent bond. So covalent bonds hold covalent compounds together. Covalent compounds are made of two nonmetals. In a covalent bond, the two nonmetals share all of their electrons. So again, in the covalent bond, the two nonmetals are going to share all of their valence electrons. This allows everyone to be stable because they're all sharing. All right, so let's look at the examples. Wait, hold on, I'll give you a minute to copy that down, and then we'll look at the examples. Okay, so let's look at the examples. For ionic compounds, we have the example of sodium and chloride. Sodium, as you know, is on the left-hand side of the periodic table, so that makes it a metal. Chlorine, which is where chloride comes from, is on the right-hand side of the periodic table, so that makes it a nonmetal. So ionic compounds are metals plus nonmetals. When metals and nonmetals join together, they form ionic compounds. Now, the chemical formula for sodium chloride is NaCl. And all we did is we took the symbols for sodium and the symbols for chlorine, and we wrote them next to each other. Now let's look at carbon dioxide. That's an example of a covalent compound. Carbon is on the right, so it is also a nonmetal. Let's get rid of the di for now and just look at oxide. Oxide sounds like oxygen, and that's also on the right, and that's a nonmetal. Now, all that this word di means is two. So dioxide just means two oxygens, just like it's shown here. If we look at our example, the chemical formula for carbon dioxide is CO2. So what we're going to talk about for the rest of these notes is how we know what goes where and which letters go where and which numbers go where. So let's go ahead and move on. Okay, so when you put elements together, you always want to make sure that they are balanced, that they're equal, you have enough of everything that you need. And there's an easy way to figure out what the ratio for an ionic compound is going to be when you have the ions. So there are two steps in your notes. Now there's a section where you're supposed to write two steps down, step 1 and step 2. Step 1 is if the charges, so that's the pluses and the minuses, if the charges of the ions are the same size, then the ratio is 1 to 1. So again, I want you to write down if the charges of the ions are the same size or the same number, you can put number in the place of size here, then the ratio is 1 to 1. What does that mean? It means that if I am calcium and I am +2, and I'm trying to bond with oxygen, which is -2, I'm trying to say I need to give 2 electrons away. Oxygen needs to get 2 electrons. Since it's the same, I don't have to add any numbers because calcium is giving 2 away and oxygen needs 2. We don't need any more calciums or any more oxygens to make them balanced. Let's look at another example. Here is aluminum nitride. Aluminum has 3 electrons it wants to give away. Nitrogen has 3 electrons that it wants to receive. So notice how we have +3 and -3. It means that this guy is giving away all of the electrons that this guy needs. So we don't need any more of him or him. Another way to think about this is what happens in, think about in math where you have opposite charges and they tend to cancel each other. So if you did +3 plus -3, you'd get 0, meaning your whole compound is neutral. It's 0. It doesn't have a charge anymore because we got rid of all the electrons we needed to get rid of and we received all of the electrons we needed to receive. So hopefully that made sense. Okay, step 2, if the charges of the ions are different, then you figure out the ratio by doing what we call the criss-cross method. So again, if the charges of the ions are different, then the ratio can be determined by crisscrossing the charges. So all that you do in the crisscross is, and we don't care about the pluses or the minuses, we just care about the numbers. So we take the number of each, this would be a 1 right there, and we move them down and across. Okay? So again, we take the number of each, we move them down and across. Let's try to reason this out. Magnesium has 2 electrons that it wants to give away. Unfortunately, it wants to bond with chlorine, and chlorine can only take 1 of those electrons, which means that magnesium is going to have an extra electron that it doesn't need. So the way we solve this problem is instead of magnesium bonding with 1 chlorine, magnesium is going to bond with 2 chlorines. So that way each chlorine gets 1 of the electrons and magnesium doesn't have to worry about its 2 electrons anymore. That's the reasoning behind the crisscross method. The easy way to do it is we take the 2 off of magnesium and we put it to the bottom of chlorine. We take the 1 off of chlorine and we put it to the bottom of magnesium and we get MgCl2. Let's look at another example. Here is potassium and sulfur. This is potassium sulfide. Now, potassium can only give away 1 electron because it's in group 1. Sulfur has 2 electrons that it needs because it is in group 16. So if this potassium gives 1 electron away, that's the only one it has, sulfur still needs another electron from somewhere. So technically we need 2 potassiums so that sulfur can get both of the electrons that it needs. But again, using the crisscross method, all we have to do is take the number and move it down. So the 2 from sulfur goes to the bottom of your potassium. The 1 from potassium goes to the bottom of sulfur. And in science and math, we don't ever write the ones because they're understood. It's like no one writes 1x because we know that x means 1x. So this is going to be the answer, K2 and S. We needed 2 potassiums so that sulfur could get all of the electrons it needed. So how do we write the numbers? And do we always write the pluses and minuses along with the numbers? When we have the ions, when we're just trying to say, okay, this is a magnesium ion or this is a chlorine ion, we do write the charges, we write the signs. But when we finally put everything together, when we write the actual formula, we do not write the charges, we just write the numbers. So the charge is written as what we call a superscript because it's written as a little number up at the top right-hand corner of your symbols, and it's going to have a plus or a minus. Once we have a formula, once we've done the crisscross, the ratio is going to be written as a subscript. So sub means that it's below, and this time we're only writing the number and we're not writing any signs, no pluses or minuses. Okay, so what does crisscross mean? Crisscross means that we take the numbers, we take the superscript, numbers, and we move them over and down. So we literally move it over and down and over and down. So again, what does crisscross mean? It means that we take the numbers, the superscripts, and we move them over and down, and we write them without the pluses or minuses. Now we do have some ions that behave differently because they're special, and they're called polyatomic ions. Now atoms, you know, are the smallest thing. They're the things that make up elements. The word poly means many, so polyatomic means many atoms. What is a polyatomic ion? It's ions formed after elements have shared electrons. So we've given some electrons away, but we still have a charge. That's what a polyatomic ion is. It's where elements come together, like we have sulfur here and oxygen here, but they're not neutral. We still end up with a charge. So it means that these two things and all their numbers kind of go together. So again, what's a polyatomic ion? It's ions formed after elements have shared electrons. So again, ions formed after elements have shared electrons. And there is a special rule that goes with these polyatomic ions. I'm going to show you a slide and see if you can figure out what they are. So how do we work with these things? The same way that we work with the ions I've shown you before. The only thing you have to remember is that the polyatomics go together. They're joined at the hip. Think of them as Siamese twins. Okay, wherever one goes, the other goes. You can't separate them. So it's still the same process. If I have +2 on this side and -2 on this side, then I have enough of everything. The ratio is going to be 1 to 1. I don't need any extra of any type of ion because I have enough. Calcium's trying to get rid of 2. The sulfide is trying to get 2. That there's enough calcium and enough sulfide to go around. I don't need to add anything more. This is no different than what I've shown you before. Now, if the charges are different, then we can still do crisscross to figure out the ratio, but here's the special rule. If you have more than one polyatomic, you have to add parentheses. Okay, so what's the special rule for polyatomics? If you have more than one polyatomic ion, you add parentheses. Okay, so again, if you have more than one polyatomic, you add parentheses. That's the special rule. So let me show you what I mean. Here we have magnesium hydroxide. Here's the magnesium, and this is the hydroxide polyatomic ion. You can't separate this oxygen from this hydrogen. They go together. Now, if you look at it, magnesium has 2 electrons that it's trying to get rid of, and hydroxide only needs 1. So just like before, we're going to need 2 of these hydroxides so that magnesium can get rid of everything that it needs to get rid of. So we do crisscross. We take our 2, we bring it over, and we write it down. We take our 1, we bring it over, and we write it down. We will end up, and this is, I'm sorry that this is screwed up right here. I'm going to rewrite this for you. We will end up with Mg1, technically, OH2. But when we write it like this, it looks like this 2 only goes with this H, when the 2 really needs to go with everything. So think of math, where you learned about order of operations, and we say whatever we have in parentheses, we do first, and whatever's on the outside of those parentheses goes with everything on the inside of the parentheses. It's the same thing in science. So to let everyone know that the 2 goes with both the O and the H, we put parentheses around them, and we write the 2 on the outside. Okay? So hopefully this makes sense. We're going to do lots of practice as soon as we're done with notes so that everyone understands. All right, so the only time we use parentheses is if there's more than one polyatomic ion in a formula. So let's look at our examples here. And how do we tell? We tell if the numbers don't match up, then we know we're going to need more of something, and we're probably going to need some parentheses if we need more polyatomics. So here we have plus 2 minus 2, that cancels, so this, no parentheses. Plus 1 minus 1, that cancels, no parentheses. Plus 1 minus 3, it's not the same, but when we do crisscross, the 3 goes on the K, and the K is not polyatomic, so we still don't need parentheses. Let's look on this side. We have plus 3 minus 2. So if we move our 3 over and down, it's going to go with our polyatomic. We're going to need parentheses there. Then we have plus 2 and minus 1. If we move our 2 over and down, we're going to need parentheses there so that that 2 goes with everything on the inside of the bracket. Then we have plus 2 and minus 3. Again, if we move our 2 over and down and our 3 over and down, we're going to need parentheses around this molecule, around this ion, because it is polyatomic, and we need to let everyone know that the 2 goes with everything on the inside. All right, so how do you tell if you have a polyatomic ion or not? Any ion that has more than one capital letter has more than one element and is polyatomic. Every time you write chemical symbols, there are lots of elements that have 2 letters. But even when you look on the periodic table, you'd notice that even the ones with 2 letters only have 1 capital letter. With polyatomic ions, because you have more than one element written together, you're going to have more than 1 capital letter. So if you see more than 1 capital letter, you're dealing with a polyatomic. So let's do some examples. Here we have Na, only 1 capital, so this is not polyatomic. Over here we have OH, we have 2 capital letters, so this is polyatomic. Over here we have H, that's just 1. Then over here we have capital C and capital N, that's 2, so this would be polyatomic. We have this is an L by the way, not an I. Al, that's still just 1 capital letter, so not polyatomic. O and H, 2 capital letters, polyatomic. C and A, still just 1 capital letter, not polyatomic. C and N, 2 capital letters, polyatomic. So I hope this wasn't too bad. We're about to do lots of guided practice that we're going to put in our notebooks, and hopefully you will really understand how these work. Let me know if you have questions.